You're back, and you want to know more about nomenclature of alkenes, so you can do really good on those assignments in Blackboard and my test. All right, so let's take a look at the rules, the formal rules of IUPAC, or the systematic name is another way that we call this, of course, right? Okay, so let's start with number one. All right, number one, guess what? You're going to pick the longest continuous carbon chain. That's how we do this. That's how we did it before. That's how we keep doing it now. So that doesn't change. That's nothing new. You already knew this. So number one, we can scratch because this is not new material. Number two, we want to make sure that number one contains the double bond. This is the new one. Previously, we didn't have to worry about this, did we? Everything was carbon to single bond carbon. We didn't have to worry about a double bond. That was not in our nomenclature. It was not in any of the examples as far as naming them or drawing the structures go. But here it is. So if we're going to name this as an alkene, then we want to pick the one that contains the longest carbon chain, but it has to contain the carbon double bond carbon. So that means if the longest carbon chain was there that did not include the carbon double bond carbon, we cannot use that. It has to include the double bond because we're naming it as a double bond. Number three, guess what? The double bond area, it needs to get the lowest number possible. If this is the only thing that is in that structure, it gets the lowest number. So this helps us to determine which end of the molecule to start numbering from. We start closest to the end with the double bond. Now, if there's more groups, and those extra groups are like amines and alcohols and things that complicate stuff for us, then our rules are going to change a little bit. But right now in the beginning, we're only focused on alkenes, and that's it. So the alkene gets the lowest group number possible. All right. Number four, once we determine this, the double bond gets a number in the name. And that typically goes in front. However, you can hyphenate the number and then put ENE at the end. All right, so that is perfectly okay. We've talked about this. I showed you an example of this. That is in the IUPAC rules. We saw this with alcohols. We saw it with amines. This is nothing new to us either. So this is old school news, nothing new. So far, the only new thing really has been number two. Lowest number possible. Numbers go with groups. Longest continuous chains. I told you it was reviewed, didn't I? Okay, number five. We also want to name any other substituent. Substituents are things like chloros and bromos and methyls and so forth, just like we did before. So you name the other substituents, and they also need a number that's associated with them as well. So ethyls, methyls, propyls, isopropyls, sec-butyls, chloros, bromos, iodos, fluoros. You know the drift. Same as before, no difference again. Okay, number six. If the chain has more than one carbon-to-carbon double bond, you still name this as an ene, but it needs a proper prefix. So, for example, diene. Di means two. Triene means three. You get the picture. So this is also going to be a new one for us, somewhat, because like we saw before, if we had two alcohol groups, we named it diol or triol. Two amine groups, well, we named that diamine or triamine. So there's really no difference there, but because it is associated with the double bond, I'm going to include it as a new rule because we've not seen double bonds before. All right. Number seven. If the chain has more than one double bond, you still want to give both the lowest number possible. Now, very often, this means that there is only one way to number the chain, and we just got to figure out a way in order to number it so both of them get the lowest group number possible. So we might see a couple of these examples. Number 7, though, is not a big issue. If you do your job the proper way, you automatically do number 7 at the same time. Number 8, all of the other substituents that we have talked about, like methyls, ethyls, propyls, chloros, bromos, and so forth, they still go in alphabetical order. That's nothing new. We've seen that before too. In the terms of cyclogroups, number 9, the double bond needs also a number, and it still needs the lowest number possible. If it's just double bonds and nothing else included, no OH groups, no NH2 groups, no ethers, and so forth. If it's just the double bond with your methyls and ethyls and chloros and bromos and stuff on them, we tend to give the alkene part the lowest number possible. And finally, number 10, if the cyclo has more than one carbon-carbon double bond, well, you still need to give it numbers, but they also need the lowest group numbers possible. All right, so all of those rules are nothing surprising, right? If you can read my chicken scratch and my lazy-handed writing onto the screen, I can write better than this, I promise, but not today. That's the kind of mood that I'm in. All right, so if you can go through these rules and you feel comfortable about them, then I think that you're going to do okay in the nomenclature section of the alkene world. Again, it's a very good review with the addition of just one or two things. Now, here's a problem. Sometimes in the world of organic, the main long carbon chain might be something different than your double bond. Okay? And we're going to run across some of these examples, so we'll see those when they do happen. And off of this longest chain, we might see a carbon double bonded to a carbon. So the question is, how on earth do we name something like that? All right? Or what if we have another group that is a carbon to a carbon double bonded carbon? That could also happen. So here's a chance where the longest carbon chain that includes the double bond doesn't necessarily include these on the sides. And I know that sounds confusing, because I just told you we include them that have the double bond. So, you know, it looks like we would go here and then into the chain and then up through here, and this is the way that we would name it. And that is the way that we would name it if there was just double bonds. But there could be other groups on this main chain that determines that this longest piece right here is going to be the parent chain. So we need those examples. We need to see what would determine that. And it just might be the case that we get these kind of groups that hang off the side. And we're going to have to be able to name those two groups. What are they called? There's a common name that's associated with them. We can also be a little bit more formal and do IUPAC names. Nobody really likes those. But if these show up, we do have a name that takes care of the whole batch. So if a carbon double bonded carbon is attached to a main chain, and we want to call this something different, maybe a common name, who knows? This is going to be called our vinyl group. So the very first thing I want you to think about is PVC, polyvinyl chloride. Well, what do you think that vinyl stands for? On the other side, we have a carbon to carbon double bonded carbon. That also is a group that shows up very commonly, and therefore we have a common name for that when it happens, and this is going to be called the allyl, A-L-L-Y-L. So I have the vinyl group, and I have the allyl group. Now, it doesn't have to necessarily be on a longest carbon chain. It could also be the case where we have a carbon double bonded to a carbon on something like a chlorine. And they would say IUPAC it. And then they will say common name it. All right, so let's use our rules. Let's use what we just learned. IUPAC. 2 carbons in the main chain, right? 1 and 2. There's 2 carbons there. So this would be called ethene because there's a double bond. I give the carbon that has the double bond the lowest group number, and I also keep in mind everything else that's attached. Well, if I number the 1 here, I can kill 2 birds with 1 stone. I can take care of my double bond at position 1. I can also take care of my chloro at position 1. So that's the way that I'm going to number this. So this is a 1 ethene, but it's also a 1 chloro. So 1 chloroethene, that 1 would understood to be there. Or if you don't like that, squeeze in another -1 right there. 1 chloro, 1 ethene, just to be safe. So there's the IUPAC way that we can name that particular compound. I can also leave the 1 off and just call it chloroethene. And the 1 is understood to be with the chloro, and the 1 is understood to be with the ene group of the double bond. But that's the IUPAC name. Well, the IUPAC name took a little bit more work because I know what I could simply call that group. That group could be called vinyl. And that takes care of all of it. And that chloro is on that vinyl group. So I could call this a vinyl chloride. That is a common way that we can name that structure. Allyl would be the same way. All right, so if I come down here toward the bottom, I could do maybe carbon, double bonded carbon with carbon and a Br. I'm leaving off the hydrogens, by the way. You know that they're there. Okay, so if I had to IUPAC this name, I've got a 1, 2, 3. So I've got a prop. I'm going to focus on my double bond because it's there. It's kind of special. Bromines happen all the time. Halogens happen all the time. Ethyls and methyls and those types of alkyl groups, they happen all the time. But this is special. So I'm going to number it this way because of that, right? There's no way I can give both of these the lowest group number, so I got to pick one over the other, and I'm going to pick my double bond over the halogen. All right, so this is going to be a propene, and it's a 1 propene if I wanted to be more formal. And then on carbon number 3, I've got a bromo group. So 3 bromo, 1 propene is going to be the IUPAC name for that structure. All right, but I could common name this, and the reason is because this group is called something, and that group is called the allyl. Look, the substituent attachment happens at this carbon here on the very end, and that is where that bromine attached to, on this carbon of the very end. It starts off with the double bond, but the group is attached to that particular carbon. So because of that, this could be called an allyl bromide. Okay? If this was an OH group that was here, I could simply call this vinyl alcohol. That's a common name. If this was an OH group that was here, I could call this the allyl alcohol. No big deal. If this was an NH2 group, I could call this vinyl amine because that's how we named them commonly, right? And then if an NH2 group was here, this would be called an allyl amine. Perfectly okay, not a problem, not an issue. So that's how we can take care of those groups if they do decide to show up for us in some of our examples. All right, so now that we know that, let's now stick it to the nomenclature. Let's show nomenclature who's the boss, right? And who's the boss? You are. You're going to be the boss over the nomenclature. You're going to tell the nomenclature what it's going to do. So we need to put it in its place. All right, so let's talk about some of these examples. Let's do CH3, CH2, CH double bond, CH2, and let's name it IUPAC. Okay, 4 carbons. 4 is bute. There we go. It's a double bond, so it's a butene. and I need to number this. I number it toward the end, and I've got to pick out the closest to the double bond. So it's here. So carbon 1, carbon 2, carbon 3, carbon 4. So at carbon number 1, I have the ene group. So 1-butene is going to be the IUPAC name. See how easy? All right, CH3, CH, double bond, CH, CH3. There we go. IUPAC it. Well, 4 carbons in total. Bute. There's a double bond. Ene. Number closest on the end with the double bond. So it's either here on to the left or here to the right. It's the same, no matter which way you go. All right, so carbon 1, carbon 2, carbon 3, carbon 4. So at carbon number 2, I have an ene group. 2-butene is going to be the IUPAC name. All right, let's do another one. CH3, CH, double bond, CH, CH2, CH2, CH3. We got to IUPAC it. All right, not a problem. No big deal. 1, 2, 3, 4, 5, 6 carbons in total. 6 carbons is a hex. This has a double bond, so it's an ene. I've got to figure out where the double bond is located. I either have to start numbering on the left or the right, one or the other, and I number closest to the end that has the double bond, and that means left. This gives me a 1, 2 position. If I go the other way, that's a 1, a 2, a 3, and a 4. So that will give me a 4 hexene. Left to right gives me a 2 hexene. 3, 4, 5, and 6. So 2 hexene is going to be the IUPAC name of that structure. Now, here's the problem. Blackboard especially, sometimes the double bonds cause it problems, and it doesn't really like to draw the double bonds when they can. So what they do is that they condense this on you a little bit, maybe to try to trick you, I don't know. But it looks to me like someone would take the time and draw the double bonds where they're going to be. And sometimes they will just not even draw the double bond, and they'll just do it like this. And it's up to you to figure out what types of bonds are present. All right, so the way that you do this carbon has 3 hydrogens and it's connected to a carbon, so this one has 4 bonds. So 4 bonds are all single. This carbon has 2 hydrogens, one to the left to that carbon, one to the right to that carbon. So this one's got 4 bonds, not a problem. This carbon, well, it's connected to the carbon on the left, it's connected to the carbon on the right, it's connected to 1 hydrogen. There's only 3 bonds to that carbon right now as it's written. And this carbon on the last one, there's 2 hydrogens, so there's 2, and then there's 1 to the carbon to the left-hand side of it. So this one only has 3. So this one's missing 1 bond, and this one's missing 1 bond. And the answer is it's not really missing. It's there. It's understood to be a double bond at that location when this begins to happen. So that's the trick that Blackboard likes to play, and it's simply due to laziness on their end, because sometimes they don't want to bother with putting the double bonds in those structures. I will always do it. I will never write it so condensed that you do not know what's there. I just don't think that's appropriate for what we need. So whenever I give you a test, the double bonds are going to be present and they're going to show up, and I'm going to write them. But keep in mind that Blackboard, sometimes it's like twisting their arm to get them to do this kind of stuff. And if you're using Mastering Chemistry, and I told you I hate Mastering Chemistry, I don't like it, but sometimes they will do it as well. All right, so those are 3 examples of alkenes and how to name alkenes. Well, let's take another one. Let's do one more before we stop the video. All right, so let's do CH3, CH2, 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 carbon, double bond goes down, CH2, and then we'll do CH2, CH2, and CH3. And we've got to name it. Now, you're probably looking at me and you're saying, oh my gosh, what did you just do to me? The last 3 were so simple. And now, look at this example. This looks nothing like the others. Yeah, it does. It does. Just don't freak out on me. And don't freak out on the test and the assignments when you see them either. You use the rules of IUPAC. That is what you do. All right, so we need to find the longest carbon chain. So some of you are going to go, all right, 1, 2, 3, 4, 5, 6, 7, 8, and this is an octane. No, 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 no. It's not. It's not an octane. It's not. Stop. The longest carbon chain has to include the double bond. So here's my double bond. This carbon is going to have to be included into that longest carbon chain. It has to. That's the IUPAC rule. So I'm going to go ahead and box around this because we have to start here at least. So I go up to this carbon and I've got a choice. Where is my longest carbon chain? Do I go right-handed and do a 1, 2, 3, 4, 5? Or do I go left-handed and do a 1, 2, and then a 3, 4, 5, 6? That is my longest carbon chain. My longest carbon chain is going to circle around like this. I'm going to circle that longest carbon chain, and this is the way that I have to name it. So now I'll go back and I number the carbons. I've got 1, 2, 3, 4, 5, 6 in total. So this is going to be called a hexene. And the ene means a double bond. Where does that double bond happen? You're only focused on double bond right now. Leave everything else off. All right, do I number to the left or do I number start from the right? I number over here to the right-hand side. This is going to be carbon number 1 right there because this has my double bond on it. And this is carbon number 2, this is 3, this is 4, this is 5, and this is 6. So on carbon number 1, that is my double bond. This is a 1 hexene right there. Okay, well, on the second carbon, I've got this group that I now have to worry about. And what's that group called? Well, hopefully you'll look at that group and you'll say, what's the name of a 3-carbon chain? And you would say, oh, Tracy, that's propyl. P-R-O-P-Y-L, propyl. 2 propyl, 1 hexene. That is the name of this structure. So do not let them try to trick you and draw these double bonds in a position that makes you think that that isn't part of the main carbon chain, because it is. It is, folks. It is. All right. So I told you we'd do one more example, but I do want to talk about one more thing, and that is a structural component to an alkene. So notice that we keep drawing these double bonds. I want you to keep in mind that this is a total of 4 electrons in this area. And there's more electrons in a double bond than there are in single bonds. So whenever a double bond happens in a molecule, this is an electron-rich area of the molecule. And electron-rich areas tend to be negative and they tend to be charged. So here you see the electrostatic potential map of 2-butene, and notice that in this area right in there we see a very strong red dense core. That is a negative area, and that negative area is going to be very attractive to anything that might be positive that's lurking around. Okay, so if something's positive and it lurks in solution and this is your kid, you're going to protect it. If not, this is going to get attacked and it's going to get destroyed. So if that begins to happen, this molecule begins to fall apart. So these double bonds are a little bit tighter than single bonds as far as how close those carbons are. But those double bonds are electron rich. And that means electron dense, and that also means reactive. So just because we say something is a little bit closer and something has more of something else, well, in chemistry that doesn't necessarily mean something good. And what I'm trying to tell you at this point is that alkenes are more reactive than alkanes. And the reason is because of that negative area that's associated with the double bonds that we're drawing. They're there. There's more electrons in that spot, in that vicinity. They are localized electrons. They are not delocalized. They're localized and they're stuck in that position right now. And because of that, that creates a very negative part of the molecule that can then turn around and react something with positive pieces. If those positives are there, that double bond is going to get attacked first. So very high electron density in these double bonds. All right, so that's where I'm going to stop the video. In the next one, we'll pick up with more examples. I just wanted to kind of squeeze that in a little bit for now, because as we start to draw these double bonds, I think it's very important for you to think about this type of stuff. Oh, there's an extra set of electrons. There's a negative area of the molecule. Therefore, that area could be somewhat reactive if given the chance. And I never really want you to lose that. I think if you do, organic becomes a little bit harder. So I squeeze this in. We do more examples. Think about this in the back of your mind as we do them, because this will become more important much later on down the road in the course.